For centuries, we imagined it as pure darkness, a void, an absence, nothing. We were wrong. This is a black hole, and it looks nothing like what you were told. A black hole is not a hole. It's not empty space. It is the most extreme object the universe has ever created. When a massive star, 20 times larger than our Sun, reaches is the end of its life, it collapses violently. In a fraction of a second, gravity wins. The explosion outshines entire galaxies. What remains is a singularity, infinite density, wrapped in the event horizon. The point of no return. Cross that line, not even light escapes. For most of history, we couldn't photograph a black hole. You cannot photograph darkness. Then April 2019 changed everything. 200 scientists connected 8 telescopes across the globe, forming a virtual telescope the size of Earth, the Event Horizon Telescope. Their target, M87, a black hole 6.5 billion times the mass of our Sun, 55 million light-years away. Not darkness, not emptiness, a ring of fire, that orange halo. The accretion disk is superheated, gas spiraling in at nearly light speed, billions of degrees. The bottom glows brighter than the top because it moves toward us, compressing the light waves. The black hole bends the rules of light itself. Gravity here warps spacetime. Light curves, orbits, wraps around completely. You're not just seeing what's in front of it. You're seeing light from every direction at once. A black hole doesn't consume light. It sculpts it. Our own galaxy has one too, Sagittarius A asterisk, for a million times the mass of the Sun, photographed in 2022. To black holes, to photographs, to windows into the most extreme physics in the universe. The universe is stranger than we imagined, and we're just getting started.
There's a fascination with the idea of a region of space having a gravitational pull so strong, nothing can escape its deadly grasp, not even a sliver of light. Well, not quite. In fact, much of what we think we know about black holes turns out to be myths. Myth 1. All black holes are black. As this photograph from the Event Horizon Telescope demonstrated, light can be detected near a black hole's event horizon. This is the boundary between normal space and the space affected by the black hole's gravity, from which no escape is possible. Part of this light comes from the black hole's accretion disk, a flat pancake-like structure composed of dust, gas, and other debris. Friction constantly moves the disk's material inward toward the event horizon. Light also comes from jet streams, which propel matter outward along the disk's north and south poles. Myth 2. All black holes are about the same size. Black holes actually come in several different sizes, which are defined by their mass. Small black holes are usually the result of a relatively short and violent collapse of a star. Recent work suggests that intermediate black holes are found in the nuclei of some active galaxies. Supermassive black holes, on the other hand, are found at the center of nearly every galaxy. Dr. Dan Evans, an astrophysicist at NASA headquarters, says, "There's a direct relationship between the beginning of supermassive black holes and the beginning of their corresponding galaxy. This strongly suggests the two were born about the same time and slowly grew in size together over billions of years." Myth 3. If you get within a few thousand miles of a black hole, its supergravity will pull you into its center. It turns out, you can get surprisingly close to a black hole. If you approached a black hole with a mass equal to our Sun's, for example, you could get as close as tens of miles. So imagine if we replaced our Sun with a black hole of the same mass. All of the planets would continue to revolve around it at exactly the same speed and distance as they do now. Myth 4. Once inside a black hole, nothing ever comes out. Nope. It turns out that radiation can escape from a black hole. One of Stephen Hawking's contributions was a theory that a black hole is not so dense in a quantum mechanical sense. The slow leak of what's now known as Hawking radiation would, over time, cause the black hole to simply evaporate. The image from the Event Horizon Telescope confirmed what Albert Einstein's general theory of relativity predicted over 100 years ago, that a black hole's form is that of a perfect circle. And as scientists learn even more about the properties of this gigantic cosmic mystery we call a black hole, they'll be able to puncture even more myths. To hear more,
most black holes in the universe are hiding. So how do we find these big, hungry cosmic beasts? Here's a clue: a space telescope with X-ray vision. Black holes are one of the biggest mysteries of the cosmos. With gravity so intense, nothing can escape, not even light. The smallest black holes we know of form when big stars run out of fuel and collapse. Then there are the supermassive black holes. Scientists don't currently know where they come from, but we do know they have up to tens of billions of times the mass of the Sun. Scientists think every large galaxy in the universe has a supermassive black hole at its center. But what role do they play in how galaxies grow and change? There are several ways to look for supermassive black holes. We can observe the way stars orbit around them. This is how scientists identified the supermassive black hole at the center of our own galaxy, the Milky Way. We can spot the powerful jets of hot plasma that are ejected as they feed. We can detect the ripples in space-time that occur as they merge. Or we can even detect the radiation emitted when stars travel too close and get torn apart. We can also spot the glowing disks of gas and dust that orbit black holes, which can sometimes resemble the approximate shape of a donut. If the donut is face on, we can see the bright disk at the center. But there's a problem. Most are only showing us their edge, and the bright disk is obscured by the wall of this donut. That's where NuSTAR comes in. The Space Telescope has powerful X-ray vision that can see certain objects or features of the universe that are invisible to the human eye. The high-energy X-rays can also penetrate thick gas and dust. Recently, we combined 10 years of NuSTAR data with measurements from other missions to sample the sky at X-ray wavelengths. We now measure that at least 35% of the growing supermassive black holes in the universe are hidden. It's important that we find and study supermassive black holes because they can teach us a lot about how galaxies grow and evolve. For example, black holes slow down star formation. If we didn't have a supermassive black hole in our own Milky Way, we would expect to have many more stars in the sky.